combating stealthy thermal covert channel attack with its thermal signal transmitted in direct sequence spread spectrum. So the speaker is Dr. Wang Xiaohang from Zhejian University. So a brief introduction of Dr. Wang. He received his bachelor and a PhD in communication and electronic engineering from Zhejian University. So he is currently a professor at Zhejian University. He was the recipient of PDP 2015 and the VSI SOC 2014 Best Paper Awards. He was the session chair of NOC's 2018 steering committee of NOC ARC 2014 to 2018 and the TPC chair of ICCS 2021. So he also served as the guest editor of the Mathematics Journal and the Microelectronics Journal. His research interests include many core architecture, power efficient architectures, optimal control, and NOC-based systems. How about let's welcome our speaker.
Thanks for a nice introduction. So can everyone see my screen?
Yes.
Okay, thank you. So today I will introduce some of our recent works on the thermal covert channel attacks. And this is the outline. And first, let me introduce some very, the foundations of the thermal covert channel. So in a TCC, we use a heat as a communication media to encode the sensitive data, that is the password, and use the heat transfer to transfer the data from source to the sink. And this is an example. We can use the high temperature and low temperature to encode bit 1 and bit 0. Usually, we use the threshold-based detection methods. We set a threshold. So if there's a TCC in the frequency domain, we can compare the signal with the threshold. If the signal is above this threshold, so we can make decision that, okay, there is a TCC attack. Otherwise, we can claim that the system is safe. However, we know that there is a direct sequence spread spectrum, DSSS for short, a technique in the wireless communication, right? So if we use this DSSS modulation to the TCC, the amplitude of the thermal signal reduces drastically to be close to the noise, and the existing detection method fails to detect it. So that's the motivation of our work. We will design a new attack with the DSSS, and then we will design a enhanced countermeasure method to detect this attack. Okay, so this is the summarize of our work. So the flow of the improved Stealthy TCC is like this. It's very similar to a wireless communication system. Instead, we do not have an antenna here. We have the thermal signal generation. That is, we run the code, the CPU intensive and idle code, to generate the temperature. And on the receiver side, instead of using an antenna, we use the sensor. For modern CPUs, each core has a sensor, so we can read the temperature from the core sensor to get the temperature data. And then we use the standard modulation and demodulation process. This is the equation for the transmitter. And for the transmitter, we we can use either OOK or FSK for modulation, and we can use the pseudo noise, this spatial sequence, to multiply this OOK signal to generate the DSSS signal. And for the receiver is the same as the conventional TCC receiver. We just use a filter to locate the interested frequency band, and then we use a threshold to make the decision to decode the signal. Okay, so this is the signals of the DSS as of the improved Stealthy TCC. So this is the original signal, and after the multiply the PN sequence. So this is output of the digital signal, and this is temperature signal that is analog. And these are the signals in the receiver. And let's look at this figure to see the magic why the DSSS can improve the stealthiness of the TCC. So the key here is like this. In the TCC modulation, we use the different heating time to heat up the temperature. And if we multiply the signal by the PN code, let's see here, effectively we reduce the heating time for bit 1, and we increase the heating time for bit 0. So here in the original TCC signal, 0 and 1, right? So the signal amplitude are very different, but now the signal amplitude are close for bits 0 and 1. And from the frequency domain, it's more obvious. As the original signal here, we have a peak, right? So we can use the threshold-based decision-making to detect the signal. But after multiplying the PN code, the peaks are much smaller, and we cannot use a threshold to make the right decision. And here you might be curious that why the detector cannot detect the signal, but the receiver can still correctly decode the signal. The reason is that for the receiver, it knows the transmission frequency. So the receiver can use a filter to filter this band. And then inside this band, the receiver can use a threshold-based decision making. And for the detector, it does not know what is the transmission frequency. So to the detector, this looks like noise. Okay, so this is a flow of the proposed countermeasure. We use a differential filter, and then we use a threshold-based decision making, and then we use the noise-based jamming scheme to block the channel. And for the differential filter, so the differential filter is to subject the amplitude of the signal of the previous time slot. So we get the delta or the increments of the signals. And by applying this differential filter, we get the differences of the signals. And then we use the threshold-based decision making, so we can correctly detect whether there is a TCC attack. Like in this scenario, we detect the the TCC, and the threshold can be determined by the following 4 steps. So this is something like statistics, and I will skip the details. And for the jamming, This is very similar to the noise jamming in the wireless communication. Once we locate the transmission frequency, we can emit a noise with the same frequency of the signal so that the signal or the channel is blocked. And now let's come to the experiments. So we have two, actually we have two different sets of experiments. One is performed on the simulator, and the other is on a real machine, on a desktop. And we will first evaluate the attack, this new attack, and let's see the bit rate versus the BR. And we compare the proposed TCC with the CODES+ISSS, so it can have an improved stealthiness and compare with a baseline TCC. So if there's a conventional countermeasure, the proposed TCC can always perform better with lower BR than the baseline TCC because the detector cannot detect it, right? Both in the simulator and in the simulator with 1 hop and 0 hop TCCs. And this is also an evaluation in the simulator and in the real machines with different channel noises. So the same results, the proposed TCC always has a lower BR. And now let's evaluate the countermeasure, the proposed countermeasure. So we can find that, okay, so if the threshold is 0.03, the detection error is the minimum. And also the sampling, the sampling number is like 2000, the detection error also is minimized. So these two results let us to choose the right detection parameters. And this is also a detailed analysis of the true positive and the true negative results. And this black curve is a total accuracy. And we can see that, okay, if the threshold is somehow between 0.03 and 0.035, the accuracy is maximized. And we also compare the proposed countermeasure with a conventional countermeasure. And we can always find that the proposed countermeasure can effectively can detect and block the improved stealthy TCC because we use the differential filter to detect, to accurately locate the signal. And this is also a comparison with the system with different system sizes. And this is overhead of the countermeasure. It's a program. It takes less than 10 milliseconds, and average power consumption is like 14 watts. Okay, so this is a summary. We proposed an improved stealthy DSS-based TCC attacks to bypass most of existing countermeasures. So in order to combat this improved TCC attack, we proposed a countermeasure which can effectively, accurately detect this improved TCC attacks. Okay, thanks. So any questions?
Any question from the audience? Please feel free to ask. Unmute yourself. Thank you.
Okay. Sorry.
Go ahead,
Yeah,
please.
go ahead.
I had one question. Thanks a lot for the great talk. You said that for the attacker, it's not possible to since the attacker does not know the particular transmission frequency. So would it be possible for the attacker to do some sort of a power analysis across the spectrum, maybe through like Fourier transform to find the frequency? Would be attack model for this scheme?
Okay, thanks for your question. Actually, the attacker knows the transmission frequency. Like for the transmitter and the receiver in the attacker, right? There are two programs. So they know in advance the transmission frequency. And that's why the receiver in the attacker can accurately decode the bits. Instead, for a detector, I mean, for the countermeasure, it does not know the frequency. So it cannot accurately detect the transmission frequency. So attacker knows, yeah.
Thank you.
Thanks.
Hi, I'm Shruti. I had a question on one of the slides. Now I don't remember the slide, but I think you sweeped the threshold. Yeah, can you go back? Yeah, this one. Sorry.
This one?
Yeah, this one. The detection error, you said the threshold was swept from 0 to 0.07. Why did you stop at 0.07?
Yeah.
Yeah, what I want to know is, so you swept the threshold, right? On the x-axis of the left figure.
Yeah.
So why did you stop the sweeping at 0.07?
Oh, okay. I see. Actually, the students also work on other, I mean, a larger value, but this curve is almost stable, and the minimum is here. So we do not draw the whole picture here.
Mm-hmm. And to what end did you sweep it to then?
You mean the largest value?
Mm-hmm. Yeah.
I think it's something like 0.1 or 0.2, something like that. And it keeps stable, and so the students stopped working on the, I mean, other values.
Oh, okay. Okay, yeah, thank you.
Thanks. Here, the reason is that we find in most of the experiments, actually you can see here in this figure. I mean, the difference are not very much. I mean, so it's not necessary to scan with larger values.
Mm-hmm. Okay, yeah, that makes sense. Thanks.
Thank you.
All right. Okay. Thank you so much, Dr. Wang, and thank you for all the questions from the audience. I think we maybe, because of time-wise, we may finish here. If you have any questions, please feel free to.
Can you send me this slide?
Okay, I expected that.
RDSA, which is composed of 4 components: 2-layer offload engine, multi-channel DMA controller, remote access processing unit, and remote access receiver. The 2-layer offload engine consists of 2 hardware protocol stacks. The lower is UDP/IP protocol stack, and the upper is command response protocol stack. The multi-channel DMA controller achieves the concurrent transmission and the priority-based mechanism to reduce the CPU consumption and improve the throughput. The remote access processing unit is responsible for handling the remote access commands in eRDC, and the task of remote access receiver is to receive the commands from both software and hardware. XI4 interface module provides a standard external interface to access the local memory and the devices mounted on the XI4 system bus. The register files module contains a set of control and status registers, which is connected to the APB bus and can be configured by the software. The command response protocol based on the UDP protocol and the command response frame. The frame header specifies the details of the command response frame. The handshake mechanism ensures that the receiver must return the response frame whenever it receives a command frame, even if an error occurs. Besides, a hardware implementation of DES encryption module is optional to provide the data security in data transfer. The remote access commands in ERDSA are divided into two types: remote memory access and remote I/O control. The former is used to access the continuous address, and the latter is used to access the one-word register. ERDSA supports two launch modes: software launch and hardware launch. In the hardware launch mode, the hardware devices can directly send the remote access command to the ERDSA, which can reduce the participation of the CPU. After this, I will introduce the experiment and analysis parts. We implement the prototype of ERDSA on the Shinix FPGA platform. And using the Shinix tools chain, Vivado and Petalytics, we evaluate the latency compared to socket-based communication for remote memory reading and writing. The experimental results show that ERDSA can reduce the latency by 54.2% and 54.6% with 1 kilobyte data, and 71.9% and 72.2% with 64 bytes data. For remote I/O reading and writing, the experimental results show that the ERDSA can reduce the latency by 74.3% and 74.9%, which means 3.76 times and 3.98 times performance improvements. Moreover, we also evaluate the CPU consumption of remote memory access. The results show that the CPU consumption of both the sender and the receiver is almost zero. Besides, we compared the resource utilization of ERDSA and the solution of ST-ROM, which is an existing scheme for the communication. The ERDSA spent about 126 resources of lookup tables, flip-flops, and VRAMs that of ST-ROM. Besides, ERDSA achieved 0.25 millijoule per megabit energy consumption with only 25 milliwatts power, which is only 52.9% that of Intel E810. And finally, I will present the conclusion of the whole work. In our work, we propose the command response protocol based on the UDP-IP protocol to realize the data reliability and security in data transfer. Next, we propose ERDSA, a solution of remote communication of embedded systems that implements a remote access controller and provides efficient and reliable remote direct access and control. At last, the experimental results show that ERDSA has lower latency, costs, CPU consumption, and power consumption compared to the sockets and other existing solutions in embedded systems. And that's all of my presentation. Thank you.
Thank you for a very good presentation. Do we have any questions from the audience? Okay, let me see the chat box if somebody has posted any question there. Okay, so I have one question. So you said you have used UDP with ERDAC. So
Yeah.
Can your design work with TCP also, or is there a reason why you chose UDP and not TCP?
Firstly, UDP has the lower complexity compared to TCP, which means that its implementation requires less hardware resources and costs. Secondly, UDP supports broadcast mode so that it can adapt to more application scenarios. And at last, since the UDP protocol does not need to establish a complete connection between the transmitter and the receiver compared to TCP. So the communication based on TCP can get lower latency. That's all.
Okay. Sounds good. Is there any other question from the audience? Okay, I think I can ask one more question. I was curious, how different is your ERDAC compared to RDMA?
I think the most differences between ERDAC and RDMA is application scenarios. Compared to RDMA, ERDAC will be more applied to battery-based mobile embedded systems, which presume the characteristics of low power consumption and latency, rather than the higher bandwidth. So that means ERDAC is more suitable for high frequency and small batch data transmissions.
Okay. Well, yeah, sounds good. I think if there are any other questions from the audience, I don't see anything in the chat box yet. So, of course, you are welcome to email the author directly, and I think we'll have a poster session as well later on, so we can discuss about those later on. Well, let's thank the speaker one more time. And I think now we can actually play the video for our first paper, that is Dr. Zhan's paper.
Hello everyone, my name is Jinyu Zhan. I'm from University of Electronic Science and Technology of China, and I'm very glad to be here to give this presentation about our work. Human voices have been widely used in human-machine interactions in recent years. Many embedded devices such as smartphones and IoT homes supports voices as input and employ speech-based authentication system to unlock or wake up. However, speech-based authentication systems are vulnerable to malicious spoofing attacks. Many researchers made efforts to detect speech spoofing attacks. However, existing studies cannot eliminate the impact unrelated to anti-spoofing. Moreover, existing studies need a longer or complete speech to satisfy the accuracy requirements, resulting in more time overhead, which may not meet the quick response requirements of embedded systems. So we proposed a segment-based detection method to identify the spoofed speeches to improve the robustness of embedded system based on speech authentication. We presented a word CQCC extraction for word segments and an average ZCR extraction for silent segments to focus on the anti-spoofing features. We designed a bias decision strategy to realize faster anti-spoofing detection to satisfy the quick response requirements of embedded systems. We conducted two preliminary experiments. First, we explored the relationship between the effective features and length of the speeches. We compared the CQCC on word speeches and sentence speeches. From these two figures, we can observe that the clustering under CQCC of words is better than that under CQCC of sentences. Then we explore whether the features of silent segments are effective for the spoofed speech detection. We extract the features on time domain. From these two figures, we can observe that the ZCR of bona fide silent segments are fewer than those of spoofed silent segments. Therefore, to realize the effective recognition of the spoofed speeches, we need to address the following two problems: how to extract CQCC of word segments and the ZCR of silent segments, how to determine whether a speech is spoofed based on word CQCC and ZCR. Based on CQCC, we define WCQCC to denote the CQCC of words. WCQCC can help the classifier to learn the features of the same words. For example, sentence XI is I am a student, and sentence XJ is student needs a pen. There are two same words, a and student. CQCC of XI and XJ pay more attention to context-sensitive features, causing that CQCC of XI is quite different from that of XJ. On the contrary, WCQCC of student in XI is similar to that of students in XJ. WCQCC concentrates the features extraction more on the anti-spoofing detection of words. Therefore, WCQCC have better performance in extracting anti-spoofing features compared with CQCC. Based on ZCR, we defined AZCR to denote the average ZCR. Then we proposed the anti-spoofing detection method based on bias decision strategy according to the results of WCQCC and AZCR obtained by GMM. We designed 4 rules to satisfy the quick response of embedded systems. Rule 1. We select the first n seconds of speeches for detection. Rule 2. A n-second speeches is divided into k segments, include word segments and silent segments. If the length of speech is less than the n seconds, the WCQCC of word segments and the AZCR of silent segments are put into the GMM classifier. Rule 3. If the classification results of the k segments are the same, the final result of the spoofed speech detection is the classification results. Rule 4. If the classification results of the k segments are different, the word segments contribute sigma votes, and while the silent segments contributes 1 vote. The final result is the classification with higher votes. If the two classifications have the same votes, the final result is spoofed. To evaluate the efficiency of our design, we conducted extensive experiments. We chose ASB Spoof 2021 logic attack as the dataset. We compared the proposed method with the other 8 spoofed speech detection methods. First, we evaluate the EER of our SASD. From this table, the average EER is the lowest among the 9 methods. We also evaluate the TDCF. The experimental results are shown in this table. We can observe that the average of TDCF of our SASD is the lowest among the 9 methods. We tested the accuracy of our SASD compared with the other 8 methods on unbalanced dataset and balanced dataset. The experimental results are shown in these 2 figures. We can observe that the average accuracy of SASD is the highest among the 9 methods. In the unbalanced dataset, the accuracy of the 9 methods decreases when the scale factor increases from 6 to 10. This is because the unbalanced dataset leads to misjudgment. In balanced datasets, the accuracy of the 9 methods increases with the growth of scale factor. Therefore, balanced dataset is more suitable for model training than the unbalanced dataset. Embedded systems usually have strict constraints on the response time. The duration of some speeches are very long, even as long as a few minutes. It takes several minutes to detect the complete speeches. This would dissatisfy the real-time requirements of embedded systems. Therefore, we made efforts to evaluate the performance of anti-spoofing detection by different duration of speech segments and obtain the optimal detection duration for quick response tasks. From the experimental results, we can observe that our SASD can achieve the acceptable accuracy for quick response tasks earlier than the other 8 methods. Since the spoofed speeches of A7, A10, and A11 attacks of ASV Spoof 2021 datasets are generated by neural networks, EER of them are higher than those of the other 16 attacks. We also evaluate the accuracy of our SASD on the latest unknown spoofed speeches generated by WaveNet, Tectron, Deep Voice, Fast Speech, and Fast Speech 2. From these two figures, we can conclude that our SASD can detect the latest unknown spoofed speeches more effectively than the other 8 methods. At last, we conducted the experiments on NVIDIA Jackson AGX Xavier to evaluate the time overhead on embedded devices. We tested the time overhead of these 9 methods with a guarantee of accuracy at about 92%. The experimental results are shown in this figure. We can observe that our SASD has the least time overhead among these 9 methods. To sum up, we proposed a segment-based detection method to focus on the anti-spoofing features rather than the context of speeches and the voice prints of speakers. We presented the WCQCC for word segments and AZCR for silent segments to extract the features. We designed a biased decision strategy to realize the evaluation of WCQCC and AZCR to detect the spoofed speeches. We conducted extensive experiments to demonstrate that our method can effectively improve the accuracy of anti-spoofing detection and satisfy the quick response requirements of the embedded systems compared with existing methods. That's all. Thank you for listening.
Thank you. Let's thank Dr. Zhan for a great talk. I think we have time for one quick question. Any question from the audience? No, I think I have a question. So is it possible to maybe include a higher order dominant features of the speech segments into the detection model that you had to maybe increase the accuracy? Or are you using only first order, to my understanding? Can you do any higher, can you use any higher order features of?
Okay, thank you. It's a good question. Include the first order or second order dominate for the silent segments maybe can increase the detection accuracy, but the number of sampling the points in the curve to calculate the first order or second order is very important to detect the silent segments. Few sampling points cannot achieve a better detection accuracy, but various sampling points will lead to a higher computational complexity. So we choose ZCR with a lower complexity to detect the silent segments. So that's the reason, I think. Thank you. Thank you,
Dr. Zhan. So yeah, I think let's move to the last talk for this session. We are running a little bit behind, but I think we should be done pretty soon. So the last paper title is Architecting Decentralization and Customizability in DNN Accelerators for Hardware Defect Adaptation. The speaker's name is Zhan. He is a PhD candidate from the University of California, San Diego. He is with the I think with the computer science and engineering department there, and he has several publications in academic conferences and journals related to embedded systems, machine learning, electronic design automation, computer architecture, and even VLSI testing. And his current research interests include resource efficient and robust hardware architectures for machine intelligence with a particular focus on deep learning. So let's invite Bruce to share his screen and start his talk.
Professor Tucker, thanks a lot for the introduction. Let me share my screen very quickly. I hope you can see my screen and you can hear me clearly.
Yes, we can see your screen and we can hear you clearly. Yeah. Please go ahead.
So first of all, thanks a lot everyone for being. My name is Zhan. I'm a PhD candidate at UC San Diego, and today I will introduce our work, architecting decentralization and customizability in DNN accelerators for hardware defect adaptation. And if you are ready, let's start. So we know that the DNN accelerators are abundant in many embedded AI systems as of 2022. But design marginalities, hardware defects, factors like aging all challenge yield and reliability of the AI hardware. And when we have defective devices, we usually have two options. First one, we can discard these devices, but this results in some economic loss and some missed opportunities. Or we can try to compensate for the faults and use that defective device. But this brings the problem of how we can effectively tackle these hardware defects. So in the previous studies, people have explored with different fault isolation techniques. So in our work, we will focus on a systolic array-based DNN accelerator. This kind of accelerator consists of a grid of processing elements. Each processing element receives a partial sum from its neighbor. It performs a multiply, accumulate, and it forwards the updated partial sum to the next unit. And when there is a defect within a particular key, this will result some of its values to be could be significantly different than the expected value. And as this difference increases, this can lead to accuracy loss in the model. So the previous work has looked into some of the isolation techniques with minimal additional configurability. So in this manner, we can bypass the contribution of that. And this will lead to a pruning manifestation on the computational model, which is much more gracefully tolerated. So for instance, in the case of input or weight stationary design, this will be activation or weight pruning. In the case of output stationary design, this will be equivalent to zeroing a partial sum. And the previous studies, they use these kind of isolation techniques, but the isolation itself can lead to accuracy loss. So they complement it with device-specific fine-tuning. So that you fine-tune the model for that particular bypass pattern to recover the accuracy. Even though this works well in practice, this has some challenges. First of all, it incurs a large training cost. So you need to able to do this for each specific fault pattern. You need to move the model to the cloud and you need to do this. Also, this has some practical challenges when the defects surface after device deployment. When it's on the field, now you need to again update the model and bring back to the device. So the main question in this, how can we minimize the accuracy loss due to hardware bypassing without needing device-specific fine-tuning? And I will try to basically outline a strategy which combines both proactive and the reactive techniques. On the proactive side, can we reduce the importance of individual variables so that when they're pruned, the model can still maintain the accuracy? And in this manner, we can boost the bypass resilience of the model with just one-time training, not device-specific fine-tuning. At the same time, can we quickly adapt to some of the bypass threat particularities on the device without needing any fine-tuning or retraining operations? And in this manner, perhaps we can improve the accuracy without needing this kind of a fine-tuning approach. So first, let's try to see how we can improve the decentralization of the model. And for this, we will revisit a well-known technique in the machine learning community, dropout and the drop connect. So these techniques are often used to improve the reducing the overfitting problem. So in the case of dropout, we train the model by randomly dropping some of these neuron outputs at every training iteration. In the case of drop connect, instead of the neuron outputs, individual weights are dropped. So this is equivalent to basically pruning some of the connections, and we repeat this for different training iterations. And DNA training with dropout and drop connect can boost decentralization and improve the model's tolerance against these pruning effects. Moreover, we can bring some of the hardware parameters into the loop as well to maximize the benefits that we can get out of this training. So how? Usually the DNA models weights are repeatedly mapped into the same computational fabric. So in this case, if we have a large set of weights, we usually tile them and map into the same fabric, which you see in the systolic. If there is one PE's bypass, this will lead to a unique manifestation of this pruning behavior. And by simply mimicking this behavior in the training phase, we realize that we can maximize these benefits. Also, DNS has a lot of parallelism. Sometimes it is possible to permute some of these variables or the computations without actually impacting the functionality. For instance, at each layer, we can diagonally shift the weight matrices, and this will lead to the exact functional model. But since this will change the mapping between the hardware and the software, this will result in different subset of ways to be pruned. And some of these subsets will lead to a higher accuracy. And we can simply evaluate some of these permutations and use it to improve the accuracy of the model. And these kind of mechanisms can be implemented at a low cost simply through shifted memory indexing when we are fetching the weights from the memory or other variables. Also, a lot of DNN models use batch norm layers. So the batch norm scales and shifts the layer outputs at the inference time. And it uses some pre-profiled statistics that are coming from the training. But if the device has some defects and bypass, these statistics will deviate. And we realize that using the values from the training could lead to some accuracy loss, which could be avoidable. And by simply fine-tuning, by simply running a few inference examples on the device and recomputing these statistics, we realize that we can improve the accuracy of the model at a low cost. And this again does not require weight training, and this can be done on the embedded device. So all of these techniques that are outlined can be seamlessly combined into a hardware-software co-design methodology. At design time, we can have accelerators with bypass logic with minimal additional overheads. And also we can train DNNs with dropout and drop connect to improve their resilience to bypassing effects. Then when a particular device has a defect, we can simply activate the bypass logic. We can deploy the model, which will give a very good baseline accuracy. And then we can complement it with on-device calibration methods. We can permute the weights, we can calibrate the batch norms to improve the accuracy even further. So here I have some results for weight station architecture. You will see different DNN models and dataset pairs at different rows. Here, the PE bypass rate indicates the portion of PEs that are bypassed in a systolic array. And we increase this value to see how the accuracy responds. And the accuracies, average accuracy is indicated with the bar charts. We have some error bars and the min-max interval as well. So here, as a baseline model, we see that the pruning effects are often graceful, but the model can start to lose significant accuracy when this bypass rate increases. We can fine-tune the model. This usually recovers the accuracy quite well, but the problem is this is expensive. We need to fine-tune for each specific device. We can train the model with standard dropout and drop connect, and this actually delivers a lot of resilience into the bypass behavior. We can bring the hardware parameters into the loop with hardware-aware dropout drop connect, and this results in a significant improvement over the standard dropout drop connect. Further, we can calibrate the batch, and this usually has a noticeable improvement. And finally, we can select the manifestation which has the least impact on the model accuracy to maximize these benefits. And the only tangible cost of these methods is on the hardware side, which we require some additional muxes in the case of input or wait stationary designs, or we need some additional AND gates in the case of output stationary designs. And the overheads are often very minimal. So in the case of muxes, we have, for the fixed point unit, we have around 7% area and 5.5% power. This is much smaller for the output stationary design and becomes much more negligible in the case of floating point units. And the delay overhead also very minimal because we introduce 1 or 2 additional logic levels. So to conclude, we have seen that how the regularity of the architecture can allow us to do effective fault isolation. At the same time, we can train models to improve their decentralization so that they operate with a subset of variables. And then we can combine with on-device calibration methods to construct a highly effective hardware-software co-design methodology for boosting DNM hardware yields, reliability, and their lifetime at negligible cost. So this is the end of my talk. Thanks a lot for listening. And if you have any questions, please let me know.
Thank you. Let's thank the speaker for his talk. Any questions? We have time for 1 or 2 quick questions from the audience. Okay, I don't see any in the chat box either. Okay, so let me ask 1 question. So can you give some examples of type of sort of hardware defects that your proposed method can handle?
Sure, definitely. I think in general, our method is very agnostic to which type of defects which could happen. This could be like a manufacturing defect to when we test the device, if there is some stacked faults, for instance, we can bypass the unit. Again, this could be perhaps some aging effects which can happen after the device is deployed. Maybe there could be some wire, basically due to some aging effects, we start to have some problems. Again, if there's some sort of an embedded test in the device, again, it is possible to address that. So usually, I think in general, if it's some sort of a permanent or repetitive type of defects or errors, the technique can handle.
So one last question. So where do you see the research going in this field? What do you think are the future research prospects?
Yeah, I think that's in some sense that's a great question. I think all of these features that I've described, some of the unique properties of the hardware, is very regular architecture, and also on the algorithm side, you have a lot of flexibility and plasticity, so that we can train models for different side objectives as well. So I feel like this probably enables a very directions for doing a very unique some sort of a hardware software co-design type of techniques to improve the reliability for these devices. And I think there's a lot of opportunities in this area. Thank you.
Very interesting. Well, yeah, let's thank the speaker one more time. I think we are at the end of the session here. But before we leave, I think let's thank all the speaker one more time and all the organizers as well as the student volunteers who have actually helped us put together this session.